Good afternoon. My name is Aubrey Undi Phiri. I'm going to give you a run through on my statistical machine learning assignment. So basically the assignment is grouped into two parts. The first part is a regression task, then the second part is a classification task. So in the regression task, we were just given data and we were told to determine the type of data that we have. So you were supposed to identify if you're dealing with a regression task or a classification task. So one thing that gave away that this is a regression task is because we had a response variable and we had the independent variable. Then the data was continuous. Then after plotting the data and seeing the relationship between the response and the independent variable, we noted that it looked something like a polynomial. As you can see, I can fit a polynomial line there. Then it tells me that I can put this into the polynomial function space, meaning that the function space of the dataset that I have was a polynomial of degree p. So this is just writing it down formally, saying the function space is of polynomial of degree p. Then the L2 loss function was used in this task because it guarantees an algorithm that optimizes the global minimum. So it would calculate the theoretic risk. And basically this would be a Bayesian learning machine, meaning that would have given the independent variable would have the dependent variable, so y given x. So this is the type of data that we're dealing with. So basically after all these, so this is actually the risk that we calculate in with the data that we have. So this is how it will be calculated, or it was calculated. Then we could estimate the model's overall complexity by using the function. So this is the function that shows the response and the deviation from the response of the predicted and the response that is known. So the deviation between the two, this is the machine that would tell us on that. So basically to create a model, we have to split the data into chunks. I would call them chunks. And basically the chunks will be called V-fault. So we have, let's say if we have let's say 100, then we can split 100 maybe into 5 fives. Okay, or we can split 100 into 50%, 50%, or we can split hundreds into 5 fourths, or we can split 100 into 2/3 or quarters, and so on and so forth. Then we would train each of those sets minus one set. Then after we get that, we calculate the risk. Then again, we would test the other set without the other set and would calculate the risk. Then we would measure how the variance differs between the different models that we have computed. So basically, our data was split into 20-degree polynomials, and for each of these we had the mean squared errors, and these are the degrees of the polynomials, and it was found that the optimal polynomial was having a degree 10. So this would be our bias trade-off, bias variance trade-off. So this is the point where we would consider the bias variance trade-off. So generally we came up with 3 models. So these are the 3 models that were taken overall. So there is one that is overfitting too much with a higher degree of about 20. Then the other one, so there's the complex model which had about a degree of 15. Then there's the optimal model which had a degree of about 10. Then there's the linear model with a degree 1. So you can basically see that the linear model does not do well of a good job because there is this part that is being left out, and we can see a lot of well performance from the optimal model. So we'll see that more with the ANOVA test, which confirms that the beta model is the one with the highest polynomial degrees. And doing a box plot test errors on the 3 models, we see that the simple model, the test error is very way up. So we would likely settle with the more complex model, though there is no statistically significance between the optimal and the complex model. So, and though the complex model is also questionable because we have these outliers here compared to the optimal model, and if I were to choose, I would choose an optimal model to a complex model, though because they're statistically significant. So the ANOVA test also says the simplest model is not a good model because it leaves out a lot of data that are not near. The deviation from the line is very, very large. So that is what the ANOVA is saying. So the second task was a classification task. We had spam and non-spam email. So basically, this is the data that we were given. So plot the distribution. We had the distribution of non-spam and spam just to see the relationship between the spam, and we see that we had a lot of non-spam, the frequency of non-spam to spam mail in our dataset, and several machines were created. So these are the 4 machines that were created on our data set, and we see these two having a small test error, the FLD and LDA, which would be referred to the QDA and this. So these two are statistically significant. So as you can see here, the test error for the FDO is tightly distributed with low, median, minimum variability. The box plot is very narrow, indicating consistent performance. So the FLD, consistent performance, same applies with the LDA. So the naive bias exude highest median test error among the models, meaning that we are having a very large variability in performance.